Good afternoon, all. You are welcome to the second week of the facilitations. So last week we started by the introduction to what we are expected to cover in this facilitation under solid state physics 2, physics 407 for this uh, season. Uh, I sent the notes, the handout for the course across to you last week, and I believe everybody have or has a copy now. So if you look at the facilitation plan for the course, we are to start dielectric properties of solids today, which is the second week of the facilitation. So in this course this week, or under this topic, we are going to cover few things like dielectric properties, what dielectric properties is, and what are the properties, or what is dielectric, and what are the properties of dielectric. We also try to look at local electric field, then try as much as possible to look at the electric constant and polarizability, and also proceed to trying to explain the concept of dipolarization and dielectric losses. So in the notes that I sent to you, if you have something like this, so these are the things you may like to cover today, like I've just told you some minutes ago. Before I go in details into what we are to discuss, we need to understand some basic things. In solid state physics, which is a branch of physics, is part of a group of a branch of physics known as condensed matter physics. So majorly what we do there is to study the crystalline nature of materials, how they behave, and in the process we use some rules, some already established theorems and equations. For example, equations in quantum mechanics to describe the behavior of electrons in a confined environment, in a bus or in a well. And also, we also look at use crystallography concept to describe the nature of these materials, likewise the electromagnetism. So basically what I'm trying to say is that most of the things we're going to be discussing are part of things that constitute the concept of solid state physics. Because in solid state physics, we have materials that are solid, liquid, and in gas. So some scientists studies solid materials alone, while some study those in gaseous state and those in liquid state. So for you to be able to understand the concept of materials, you need to understand the crystalline nature of the materials. That will give you an idea of what the material looks like and what can you use the materials for. Likewise, you need to understand a concept uh, that has to describe the way electrons are in the materials. In the process, we'll be talking about the conductivities of the materials, then the insulating properties of the materials. So if all these things are known, then it will be very easy for us to identify materials and specifically say that this material can be used in social industry or can be used in social applications. So if you have taken your time to go through the note, you will see that on page 10 of the note, we have conductor. So the question is, what is a conductor? And we also have insulators and dielectrics. What are these things? So conductors are, are those with electrons which are free to move in the presence of a field. That is, these are electrons that can move freely once you put the materials inside a field. An example of these are metals and carbon. They have electrons that can move freely in the presence of a field. We also have insulator and or dielectrics, which is the main content of what we are going to discuss today. So insulator, most of us we are familiar with these things, but we don't know the physics behind it. You know, at home, in the kitchen, our Mothers, sisters, wife uses spoon for cooking. And if you look at the spoon, at the end of the spoon, there is always a solid material like a rubber, black in nature, that they use to wind the end of the spoon. So this thing is known as insulator, and the reason is that it doesn't allow the flow of electrons. So those in which the electrons are strongly bound to the atom or molecule compose the material and cannot be detached by application of electric field. Of this example of this are sulfur, propylene, mica, and this thing. So these are the materials that has this concept in them, insulating properties. So we go straight to the bone of a contention for today's class, which is dielectric properties. So we ask, what is dielectric? A dielectric is a non-conducting material such as glass, rubber, or wax paper. So if we say that a dielectric is a non-conducting material, that is the material that cannot allow the flow of current to pass through them. If, like I gave you an example some minutes ago, if you hold a spoon with a black rubber that is wound around it, you will see that if the spoon got hot, you will not feel the effect of the hot, because normally the heat will flow through the metal down to that point. But once you get to that point, because an insulator doesn't allow the flow of current or electricity or electrons to move up, you will not feel the effect of the heat. So if we now know what dielectric is, now what are their properties? So now the first one here is that when a dielectric material is inserted between the plate of a capacitor, the capacitance increased by a factor K called the dielectric constant of the dielectric. So what we're trying to say is that we have two capacitors and two capacitor plate, and you now insert a dielectric materials in between it. It is a more or less of trying to increase the capacitance by a factor, and that constant is known as dielectric constant of the dielectric. So that gives us this equation. So this C here, C naught, is the initial capacitor, and the C naught is the capacitance in the absence of dielectric. So when there is no dielectric, you don't have this C. When there is no dielectric, you have this C naught. But when there is dielectric, it changes. So the second property there is the dielectric constant K. It has no unit because C here and C naught here, both of them are measured in farad, microfarad. If you divide them, the unit will cancel out. That make K to be a non-unit constant, and it's characteristics of a given material. So we also have, if epsilon is the permittivity of free space, this epsilon naught is permittivity of free space, and epsilon is permittivity of the dielectric material. So if we relate these two quantities together, you can also have the dielectric constant, which is K is equal to epsilon over what? Epsilon naught, which is equation 1.2 here. Likewise, when you introduce dielectric material, the energy density becomes this. So once you introduce a dielectric material, it possesses energy, and the energy density can be written in this form: U is equal to half epsilon E squared. E here is the electric field. So the potential difference V between the plate when a dielectric material is inserted, provided that the charge remains unchanged, is given as this: V is equal to V naught over K, where V naught is the potential difference when the dielectric is not inserted. So V naught is the potential difference when the dielectric is inserted. So equation 1.4 states that the potential difference V between the plate decreases by a factor K. So also, if the potential difference is kept unchanged when the dielectric material is inserted, Wálé, mo ṣì wà nínú school, má worry. So when the dielectric material is inserted, then we have Q to equal to K Q naught. Thus, the charge of a capacitor with a fixed potential difference between its plates is increased by factor K. So meaning that this is more or less like a direct proportionality, a direct relationship between the charge when the dielectric is inserted and when it is not inserted. So also, if the the electric field between the parallel plate capacitor E naught and it is E after the material with dielectric constant K is inserted into the space between the plate, then we have this equation 1.6. So from equation 1.6, we see that the electric field within the dielectric is reduced by a factor equal to dielectric constant. So we see that the relationship between all these quantities is direct in nature. Now, if you now look at the net field E within the dielectric is given by this. That is, in the presence of electric field and in the absence of electric field, you have a net field, which is E, which is now equals to E naught minus E induced. So E naught in this case is the original electric field. That's the original field. And E induced is the one generated as a result of electric field induction. That is, when you inserted or when you try to bring in the dielectric into the system, you have E induced because this is generated as a result of the presence of another uh, parameters. So if you combine equation 1.6 and 1.7 together, we have this. So the induced electric field in the dielectric is related to the induced charge density this through the relationship this. So from equation 1.9, you have this, which is charge density of induced to be this, and the charge induced to be this. So technically speaking now, we can say that Q, charge density induced over Q, which is going to be 1 minus 1 over K, is the same thing as charge induced over Q. Because if you make this formula, two of them are equal. So since K is always greater than 1, this expression, that is equation 1.8, 1.9, show that the electric field induced is greater than this, and charge induced is greater than the charge density induced is greater than this, etc. Any questions? Does anybody have questions? Okay. Now, let's look at another concept there, which is local electric field. The local electric field. So now, we said that one thing that we should know is that every material is made up of a very large number of atoms and molecules. This we know. An atom consists of a positively charged nucleus and negatively charged electron. We are all familiar with this. 4. A system consists of two equal and opposite charge Q separated by a distance D is an electric dipole. Fine. The last one is when an atom or a molecule of dielectric is placed in an electric field, the positive and negative charges feel opposite forces and are separated, forming a dipole. What we are trying to say is that if you have two charges with different charge, you have atoms or molecule of dielectric with different charges, positive and negative, there is possibility for induced forces that are separated as a result of a dipole that will form between them. So now let's look at this. Suppose the charges minus Q and plus Q are placed respectively at distance d over 2 and minus d over 2 from the origin, as we have in this figure. The magnitude of the potential due to this system at a point S is given by this. So this is the magnitude of the potential. So the question now is that if you look at this, we have minus Q and plus Q. Then to a point X. So from the negative charge to point X, the distance of restriction is R2. From the positive charge to X, the distance of separation is R1. So now, we now have a kind of a triangle. So from this place, if we put all this into consideration, we can derive this expression. Let's see how it goes. So we say if theta is the angle between the axis of the charges and the position vector of X, we can write 1 over R1 to approximately 1 over R plus d cos theta 2R squared. The same thing for R2, we have this. So if you substitute this in equation 11 here, 1.11 here, this place, the value of 1 over R1 and 1 over R2, definitely we are going to have this expression. So the dipole moment P is the vector along the axis of the dipole, pointing in the direction of minus Q to plus Q and having magnitude QD. So in terms of dipole moment, you can see that equation 1.12 becomes this. That is, when you bring in the dipole moment of the system into consideration, we have this equation we can write in this because QD, which is this, will give us P bar dot R bar. Hope I'm making sense. Now, if you look at this now, using the grad of this, the grad of 1 over R, it will give us this. So the equation 1.13 can be written in this form now. Instead of this now, you can now have, because the whole of this now, this over this is like this. So we cannot substitute it with this, and that gives us this. So where phi naught is the potential of a unit charge. So the field of an electric dipole may also be expressed in the following way. We can also write the field in this form because electric field is the gradient of the potential. So this we have this expression. And you just like doing algebra here, then you have this as a final result. So now, any question? Do you have any question there? Anybody with any questions, you are free to ask me. Okay. If there is no question, now considering a cubic crystal dielectric and assuming an electric field of magnitude E naught is applied parallel to one of the axes of the crystal. So the field will push the positively charged nucleus of the atom of the dielectric slightly in the direction of the field and negatively charged electron in the opposite direction, as we have it in figure 1.2. We say that the atom is polarized under the influence of the applied external field, and the charges are called polarization charges. So the polarization P is defined as the dipole moment per unit volume. Average over the volume of a cell, the total dipole moment is defined as this. So, do you have anybody with any questions? Any questions? Okay. In the absence of no questions, I think we will stop the lecture here today and we continue from here